enter the GM tube. But our question is, what is the total activity of the radiations that are being emitted by the source in general? Because it's not like all the radiations that are being emitted by the source in the general are able to reach the GM tube so that the counter or the retimeter can give us a reading in order for us to calculate this. So I'm going to use this mathematics to calculate that value of the activity of the source. Activity detected. Activity detected by the GM tube. I think it was 75. Yeah, that one is 75 counts per second. So this one is 75 counts per second. So what is the activity of the source? It means that 1.257 exponent 3 divided by 5 must give me the activity of the source divided by 75, which is the activity detected. So activity of the source using this mathematics is 75 divided by 5 multiplied by 1.257 exponent 3, which must lead us to yeah, 1.886 exponent 4. Counts per second. Number of atoms disintegrating per second. From the source is 1.886 exponent 4. That is the solution to Roman 1. Now, what is the half-life of the source? Remember, I know the activity of the source. And for those of you who have been with us from the start, you remember we saw the relationship between activity and number of atoms disintegrating. If I know the number of atoms, of which I can, why? I have been given the mass number of the radon, and then I've also been given the weight that is involved in emitting those disintegrations per second. They said 1 gram is what was placed 10 centimeters from the GM tube. So, in order for me to answer Roman 2, I'm basically going to evoke that equation. Activity is lambda n, where n is the number of atoms. I gave you a formula for n, which even me, I cannot remember right now because I told you I'm not very good at cramming formulas, but I'm going to go through my method of past principles, then I'm going to know the number of atoms that are present in 1 gram of this piece of radon. So, I want to put a however, 22 grams of the radon 222, we know according to Avogadro's theory, contain 6.02 exponent 23 atoms. So the 1 gram will therefore contain 6.02 exponent 23 divided by 222 atoms. So this number of atoms now present according to my calculation, I'm having around 2.712 to 3 decimal places, 2.712 exponent 21 atoms. So, what is lambda? Lambda, we know that lambda is natural log 2 divided by the half-life. So if I know the activity and I know the number of atoms present, it means that if I substitute for lambda as natural log 2 divided by t1/2, then I'll be in position to get the half-life of this piece of radon. Thus, A natural log 2 n divided by t1/2 such that t1/2 is going to be defined by n natural log 2 divided by A. So t1/2, which is the half-life, will now be 2.712 exponent 21 multiplied with the natural log of 2 divided by the activity, which is 1.886 exponent 4. So since I'm having an activity which is per second, and my half-life is therefore the figure 9.967 exponent 16 seconds, because I'm using an activity of per second. So that is it. So I want to congratulate those people who made notes and indeed went on and researched about the whole procedure and experiments on determining the half-life of radioactive elements using the ionization chamber and then also using the Geiger mirror tube. That is to say, determining the one of a short-lived material and then also the one of a long-lived material. In case you're wondering why, I hope people still remember why we need information on the half-life of any radioactive element, because it will help us deduce very many things. For example, its activity, since it has a relationship with activity as given by that equation. Since I'm soon winding up this part of radioactivity, in fact, next week I'll be sharing a list of those people who have continuously responded to all the assignments that I've been giving, both for O-level and for A-level. I think we need to really credit them, because I know there are some names which, for every assignment that I leave, they keep mailing me, they keep giving me feedback. I really need to upload those people to the general public. So I promise that next time I'll come with a list of those people. So using this very set of procedures, I know that members out there who have been following me will be in position to go through them and then also arrive at the required calculations for the other number, because the two numbers are similar. If you can read through it, you will see, because we have, this time they're being specific that the source is emitting alpha particles. A tiny mass of that element, mass number has been given to 41, mounted 7 centimeters. This time, this is 7 centimeters in front of the GM tube. Retimeter connected to the tube reads 5.4 exponent 4. So that is the activity detected by the GM tube. Only that this time it is per minute. Then if the number of atoms in the sample is 5.8, then calculate the number of disintegrations per second. Now that is where the trick is. There is count rate reading being given in per minute, then asking for number of disintegrations per second. But I know that is just basic mathematics of conversion and units. What is the relationship between a minute and a second? Of course, 1 minute is equivalent to 60 seconds. People will be in position to play around with the math and then arrive at this solution. Kindly share with me this solution through my email, lutherken@gmail.com, or our general email still we shall receive. Somera Muddiiro @gmail.com. I know there are some people who try to send here and then probably does not come, but always the person operating the other email forwards, because now the emails are so much crowded. You get a lot of messages, hit the limit, you cannot receive anymore, but I keep deleting. So if you try this and it fails to come, kindly forward it through the second email. Now, going back to what we are supposed to be discussing today, I wanted to make a continuation on my calculations that require the use of Einstein's equation, binding energy, and the likes. I'm going to do this question. I hope that people are through with this. Allow me to write it down. Last week, I calculated the energy released by released during the decay of radon. I gave that energy. Today, let me go through this. I hope people are through with this. So my today's question on binding energy reads that given that, given the information below, determine the binding energy of the helium nucleus. So they are telling us that the mass is 4.028U, and then the mass of a proton and then the mass of a neutron so but when you look closely, this number is like the example which I did last time. Then maybe let me also give the question which is in the question bank with an error, but with the error corrected. That question reads that find the binding energy per nucleon let me phrase it like this. Calculate the binding energy for iron 5626 nucleus, given that mass of 1 neutron 1.008665 U, proton 1.0 007277 U, the one of the iron 56 itself 55.9349, full stop, 1 U 931 mega electron volts. You will apply this very figure on that one. So those are also questions for you to try out. So I hope you're through with this. These examples, sorry, the numbers which I've given are familiar to the first example which I did. Now, the number which I'm going to do with you, and then later on I'm also going to leave you an assignment of a number which is almost the same, is this. Consider the nuclear reaction below. I have uranium 235, 92, 0, barium X56, krypton 89 plus 3 neutrons plus energy. So the question is Roman 1, find find the value of x and y. Roman 2 is to calculate the energy released by 1 mole of the uranium-235 in the above reaction. And then lastly, okay, the last part is it's a theory part where they're asking us to explain why neutrons are preferred to charged particles for inducing nuclear reactions. Okay, let me give it. For inducing nuclear reactions. Now, we are towards the end. That's why you see that I'm trying to go through the remaining questions, and then those ones which I come across and I see that I've already done an example which is familiar, I'm leaving for you as assignment. But of course, when people reach me in my email, I will be sharing more numbers outside this. So this is my nuclear reaction which I have. I have uranium-235 being bombarded by a neutron, giving me this element, unknown mass number, probably beryllium. And then we also have this unknown atomic number, and then 3 more neutrons plus energy involved. So find the value of x and y. We know that any nuclear reaction must be balanced in terms of the masses from the reactants. Sorry, the mass number of the reactants must be equal to the mass number of the products. And then also the atomic number of the reactants must be equal to the atomic number of the products. So straight away, we have that 235 plus 1 must be x plus 89 plus 3 times 1, because there are 3 neutrons that arise from that nuclear reaction. So I have 234 being equivalent to x plus 89 plus 3, that is 92. Then I have x becoming 234 subtracted, 234 minus 92. Get 142. Sorry, this is 236. 235 plus 1. 236 minus 92. You get 144. Moving on, atomic numbers, 92 plus 0, 56 plus y plus 3 times 0. So y is basically 92 minus 56, which is now going to reduce to 36. Yes. 92 plus 0, then the other one is 56. 3 times 0 is 0. So the value of y is 36. So those are the values of x and y. Now, what is the energy released by 1 mole of uranium-235 in the above reaction? Oh, I forgot. They gave me the masses. Sorry. Let me give them. They gave me the masses of the uranium 235, the mass was given. This they will always give. If not given, then you should know that is just an error in typing. Then they also gave me the one of a neutron. This was given at the end of the question, 0090U. Then they also gave me the one of the barium X. It was given as 143.9577U. Even the one of krypton 89 was also mentioned as 88.926U, and then 1U was represented by 931 mega electron volts. So this information was given. Sorry, I did not give it from the start, but it was given. Kindly write it down very fast, because I want to go on and then calculate first of all the mass defect, considering the total mass of the reactants involving the neutron that was bombarded with the uranium-235. Then I want to go on and also calculate the total mass of the products that involves the Ba, the krypton, and then also this. And then after that, I want to use Einstein's mass energy relationship to find the energy associated with that mass defect. But the energy associated with this mass defect will be equivalent to one atom, because it is what was bombarded with a neutron. So they're asking me the energy released by 1 mole. So according to Avogadro's theory, 1 mole of the uranium-235 contains 6.02 exponent 23 atoms. So the energy which I'll get there, I want to multiply on the 6.02 exponent 23 atoms, and then that will be the energy associated by 1 mole of 235. This is what I'm saying. These calculations are usually basic. Mass of reactants. That is the mass of uranium-235. This one I've been given as 117U. Mass of the neutron is 1.0090U. So add that. Then mass of the products. The mass of the products, I have the one of the Ba, which is 143.9577U. The krypton, that is 88.926U. Then the 3 neutrons, which come in excess, that is 1.0090U. So quickly we'll go through this. 235.117 added to 1.009, I get 236.126U, then 143.9577 plus 88.926 plus brackets 3 times 1.009 gives me 235.917U. So what is the mass defect? The mass defect is definitely the difference between the mass of the reactants and that of the products. This will be 236.126U, 235.9107U. I hope my mathematics is perfect. 957, 88.926 is it what was given? Yeah. But then, yes. So I'm going to subtract those two. That is 236.126 minus answer. I have a mass defect of around 0.2125 0.2153 U. So what is the energy associated to this mass defect? All these calculations are like this. No tricks. This energy, according to Einstein's mass energy relation, is multiplied with 931. Why? Because the examiner has helped us. He has already given us the energy associated with the mass defect of 1 U. So if this is the mass defect that I'm having, so I'm just multiplying this to get the energy in mega electron volts. So when I feed this into my calculator, I get energy which is around 200.4443 mega electron volts. So I can deduce that energy in mega electron volts because the examiner did not dictate in 1 units, he wants the energy, or I can choose to go by first principles, and then I multiply the 1.6 exponent minus 19 representation of 1 electron volt, and then I also multiply with the 1 exponent 6 representing the mega. Then I finally arrive at 3.207 exponent minus 11 joules of energy. How have I arrived at this? I multiplied with the 1 exponent 6 mega. Then I've also multiplied with 1.6 exponent minus 19 representation of 1 electron volt in terms of the joules. Then that's how I've arrived at this. I'm sorry I've not shown that part, but I'm hoping that people are following me on it because we've been doing this over and over again. Now, but I say that this energy is associated with 1 atom because it is what participated in this nuclear reaction. So, if I instead go to the energy associated with 1 mole, how many atoms are contained in 1 mole? So, lastly, according to Avogadro's theorem, 1 mole of the uranium-235 contains 6.02 exponent 23 atoms. Thus, the energy released when 1 mole participates in the above nuclear reaction will now be 6.02 exponent 23 multiplied by 3.207 exponent minus 11 joules. So, thank you for being good followers. Because of time, we do not have any more minutes in order to answer the last part, but I'm very sure that people who have been following us, the last part we've ever answered at the beginning, I explained why the neutrons are preferred to any other charged particle in inducing nuclear reactions. Until next week, I'd like to sign out and wish you the very best of the remaining part of today. Kindly reach me in my email and all the other platforms. Thank you.
Owange jebaleko okuteko ku ssente leero munyoluka mmotoka yo olinnya lifuti oba okute ku mapesa ga kompyuta yo ku mulimu olinago okutekwa mu ngalo oba ku ssimu yo yennyini weetaaga skin guard hand wash soap ne sanitizer linda ku katono tunuuya engalo zo oziraba oyinza okuba okutte ku kintu ekiriko obuwuka bwa coronavirus kubanga busobola okwekwekako okumala essaawa nnyingi nnyo kati nno wulira amawulire amalungi weetaaga skin guard hand wash soap ne sanitizer